We will now continue the course with the continuous to discrete transformations. It's an important subsection, and it could very well be that at the time of the exam you have an exercise where you have to apply one of these continuous to discrete transformations to a given transfer function. We will now start this subsection with the impulse invariance method. The idea is very simple. So you're given a transfer function h of s and you want an equivalent discrete time filter, and we'll call it like this, and I here is for impulse invariance, and you want to construct this discrete time filter in such a way that the associated impulse response corresponds to the impulse response in continuous time, and that both of them match at the sampling instance. Okay, so this is the impulse response associated with this discrete filter. This is the impulse response in continuous time, and they have to match at the sampling instance. Okay, so if you kind of take the z transform on both sides, right, and multiply by ts, you have a way of obtaining this equivalent discrete time filter using the impulse invariance method. So you take your transfer function, you compute the impulse response h of t, you sample it so that you obtain h of k, and then you take the z transform and you have to multiply by ts. This factor ts is sometimes forgotten in even reference books, and we'll kind of look now where it comes from. For instance, if you go to Matlab and type help impulse, you will see that for discrete time systems, the impulse response is the response to a unit area pulse of length ts. And since we have a unit area and the length is ts, the height must be 1 over ts. And this explains here that you have here indeed this factor 1 over ts. So here is the interpretation. In here we assume that both convergence, analog to digital and digital to analog, are ideal. So at the input we have here x of z 1 over ts. This corresponds to an impulse, discrete impulse multiplied by 1 over ts, and again associated with a sampling period of ts. This shows that the area under the curve of this one is indeed 1. Okay, so if we have here an ideal conversion digital to analog, well, the equivalent continuous signal that you would have over here is a Dirac impulse, and remember that the Dirac impulse has indeed an area under the curve of 1. The Laplace transform is here x of s is equal to 1, so this is x of s. It goes through the system, and of course you have y of s is h of s, x of s. So in this case you're left with this one. Okay, so if you have an ideal analog to digital conversion, what you will have here at the output, well, is the inverse Laplace transform. This is h of t evaluated at t is equal kts. This will produce you h of k, and then you take the z transform, and you remember that the transfer function is the z transform of the output divided by the z transform of the input, and indeed we obtain what we have obtained in the previous slide. So here is an example, but before we start, you have to, of course, be able to work with the Laplace transform and compute inverse Laplace transforms. So this presupposes that you kind of know all these Laplace transform, or that you're able to find them, and that you're able to take, well, partial fraction expansions. we'll work with this transfer function here. That is the transfer function of a first order system with static gain 1. The static gain can be obtained by replacing S by 0. So the impulse response h of t is simply obtained by taking the inverse Laplace transform, and you'll obtain a exponential of minus at u of t. So if you sample this signal, you obtain the following sequence, okay, and this is rewritten differently. You remember that the z transform of alpha k uk is z over z minus alpha. I always say remember, but you should be able to find this back, well, using the definition, okay, and this slide with the fundamentals of the z transform. So if we take the z transform of this one and we multiply by ts, this is what we obtain. Okay, so this is the impulse invariant equivalent discrete time description of this system over here. Notice that the static gain over here is ATS 1 over exponential of minus ATS. You remember that the static gain in discrete time is obtained by replacing z by 1. Okay, so you can observe that the static gain is not 1 in this case, but if ts becomes small, then, well, this will tend to 1. Remember that exponential of x is approximately 1 plus x plus, well, of course, additional terms. We'll just use the two first terms over here, so that this one becomes ATS over, well, approximately becomes 1 minus 1 plus ATS, right? So these ones will cancel out, so this will be 1. So this one here is approximately 1 when ts is small. Okay, so you can see here that the static gain is not 1 in general, but that it will tend to 1 if ts tends to 0. Well, the calculations that we have just done, you can do them in Matlab using the symbolic toolbox. So this means here that all those variables are symbolic. So you enter your transfer function, you take the inverse Laplace transform. So here, in this case, you have the continuous time impulse response. You replace t by nts. So this is really sampling. Here you have the impulse response, but in discrete time. Then you take the z transform and you multiply by ts. So you'll have the same expression. So you can really use the symbolic toolbox to obtain an impulse invariant equivalent process, right? And the advantage of doing this is that you have the, well, description as a function of the parameters and ts. If you use the command C to D, of course, you have the expression, but in a particular case for certain values of the parameters and a given value of ts. So this can be something that is interesting if you really want a description that is ts and variable dependent. So here are some results with this transfer function h of s that we have considered, a over s plus a. Here we have given a the value 5. We kind of discretize with ts is equal to 0.1. So this is the code to enter the continuous time system. You could of course use the command C2D, but here we want to check our results, right, and have a look at the step and impulse responses. If you use the command C2D, continuous to discrete, you have to enter your continuous time description, give the TS that you want, and then the method and the impulse invariance method, what you can use in Matlab using the argument impulse, right? We will not do this. We will check our results. Those are the results that we have found previously, and then we compare the continuous time and discrete time step responses and impulse responses. Well, we know that by definition the impulse responses should match at the sample instance. And we see that this is indeed the case. In blue you see the continuous time impulse response, and here the impulse response associated to this impulse invariant discrete time description of the system. And as you can see, they coincide, they match at the sample instance. Here you have TS is equal to 0.1. Here we compare the continuous time step response here in blue and the one that we have obtained using our impulse invariant, the equivalent description of the system. And you can see here that they do not match. Well, of course we know that they do not match because we have seen that the static gain of the system was ATS over 1 minus exponential of minus ATS. If you plug A is equal to 5 and TS is equal to 0.1 and you do the calculations, you will see that this is approximately 1.27, and indeed this is what you can see over here. Okay, but what we can do now is do the same kind of experiment with a TS that becomes smaller and smaller, and you will see that then also the step response of the equivalent impulse invariant description will start to match better and better with the continuous time step response. What you see over here is the code that I have shown you in the previous slide. If I run it, you of course obtain the impulse and step responses that I've shown you. The idea here is now to divide TS by 10 and run the same code, and then you see here that the impulse response by definition still match at the sampling instance, but with a TS that is smaller, well, you can see that there is a difference in the step responser, but the match is of course better than when TS was 10 times larger. Okay, so if I divide by TS by 10 again and run the code, well, of course the impulse responses, if you zoom, still match at the sampling instance, but now you can see here that the step response almost matches as well. So in conclusion, using this impulse invariant discretization method, you always ensure that the impulse responses match at the sampling instance, whatever the TS, but the step response will only match if TS is chosen small enough. So we'll now obtain a different method, which is called the step invariance method. We'll see that it's also equivalent to the so-called zero order halt method. So the idea is that you're given a transfer function in S and that you're looking for an equivalent discrete time filter transfer function in Z, and here SI stands for step invariance. Okay, so the idea is that, well, the step response associated to this one corresponds to the step response associated with this one at the sampling instance. So the step response associated with this one is really, well, you have to multiply by the Z transform of a unit step, right? So this is the step response in the Z domain, and you take the inverse Z transform. The step response associated to the transfer function in S, well, you multiply by 1 over S, take the inverse Laplace transform, and then they have to match at the sampling instance, right? So if you take the Z transform on both sides and you multiply by 1 over 1 minus Z minus 1, you obtain the method or the equation that will allow you to find this equivalent discrete time filter. So this is the interpretation. At the input, well, you have a unit step in the Z domain, Z over Z minus 1. This unit step, if it goes to an ideal digital to analog conversion, is a U of t. Laplace transform is 1 over S, so the response here is the step response, okay? If you go through an ideal analog to digital conversion, really what you obtain, well, is the continuous time signal, right? So this is the Laplace inverse transform of H of S divided by S, and then evaluated at t is equal to kts, and y of z is then the z transform of that, well, discrete time sequence. The transfer function is, well, the z transform of y of k divided by the z transform of x of k. This is what you obtain, and you can rewrite it like this if you're using the variable z minus 1 instead of the variable z. We now look at the zero order hold method to obtain a discrete time equivalent, and we will see that it will be equivalent to the step invariant equivalent discrete time description. So the idea here is that the discrete time impulse response, okay, remember that it's a unit area discrete time impulse response, so we have a height of 1 over ts that is held for ts. So this is the discrete time equivalent impulse response, must correspond to the zero order hold held impulse response of the continuous time system. So what we do over here is take into account the analog to digital and digital to analog conversions. Okay, we have seen that if you have both in sequence, the equivalent transfer function is given by this transfer function over here. Okay, so if we take the inverse Laplace transform, we have the so-called, well, impulse response that takes into account the analog to digital and digital to analog conversion. And now we have to make sure that this impulse response corresponds to the discrete time impulse response. So what we can do now, because we have linearity of the Laplace transform and the Z transform, we can cancel out the TS and the 1 over TS over here and take the Z transform on both sides, and you obtain the expression of the zero order hold discrete time equivalent filter of this transfer function over here. We can now show that it is indeed equivalent to this, well, step invariant discrete time equivalent. If we define S of S as H of S divided by S, so the Laplace transform of the step response, because of this quantity over here, 1 minus an exponential of minus TSS, really this, if you take the inverse Laplace transform, what this will give you is, well, the step response minus the step response delayed by the sampled period Ts, right? If you evaluate in t is equal to kts and take the Z transform, well, you'll have obviously a factor 1 minus Z minus 1 that will appear. The 1 comes from this one, and the minus z minus 1 comes from this one. It's the same signal but delayed by one sample period. So remember that z minus 1 is really indeed delaying by one sample instant. Okay, and what we'll have over here is of course s of t. So we see here that the two equivalents, the one obtained by the zero order Holt method and the one obtained by the step invariance method, are indeed equivalent. We'll use the name zero order Holt method. Okay, and it is really this method that you should use if you're going to do a so-called direct digital design, so a design based on a discrete time description of the system. This discrete time description should take into account the zero order Holt mechanism. So here is the interpretation. We have at the input a signal that is 1 over Ts delta k, right? So its Z transform is 1 over Ts. We take an unit area impulse, so it has a height 1 over Ts. The sampling period is Ts, so indeed you have a unit area. So by taking an ideal digital to analog conversion, well, you'll have a signal over here that can be approximated by x of t delta t. Okay, so its Laplace transform is 1, and you can model the whole chain analog to digital followed by digital to analog conversion by this transfer function over here. Okay, that multiplies the transfer function of the actual system. So if you assume analog to digital conversion, okay, well, the discrete time signal that will come out is really the Laplace inverse transform of this quantity here, evaluated at t is equal to kts. And if you're interested in y of z, then you'll have to take the z transform. So the transfer function for this ZOH equivalent discrete time description, right, is y of z divided by x of z, and what will happen is that the 1 over ts here and the 1 over ts here will cancel out, and indeed you obtain the following equation. We have shown in the previous slide that it is equivalent to this formula over here, and this is really the formula that we'll use for this ZOH method, okay, which is also what will be used for the step invariance method, because both methods are indeed equivalent. So what you do is compute the step response. So h of s divided by s Laplace inverse, that's the step response. You sample the response, t is equal to kts, you take the z transform and then you multiply by 1 minus z minus 1, okay? Or you could multiply by z minus 1 over z. It all depends if you work with the variable z minus 1 or with the variable z. So this representation that we have here, we have obtained it because we have worked with a unit area impulse at the input, height 1 over ts, width ts, so it's a unit area discrete impulse, and the equivalent impulse in continuous time will simply be a Dirac function, which is also a unit area under the curve. So the equivalent Laplace transform is 1, and we know that an ideal analog to digital followed by digital to analog conversion can be modeled by this transfer function over here. This is something that we had seen at the end of section 2. What we see now is when we compute the transfer function over here, that the 1 over ts cancels with the 1 over ts. So this is a bit annoying to work with this T1 over Ts, for instance, in here. So what we can do is, instead of working with a 1 over Ts here, work with a 1 over here. Of course, then we do not work in discrete time with a unit area impulse, because the height is 1 and the width is Ts. So it's a discrete delta with area Ts. But if we do this, we have a Ts over here that can cancel out with this one, okay, and therefore it will also disappear in here, and of course the result will be the same over here. This is what is shown in the next slide. Okay, so this means that we can cancel out over here, right? And in the next section we'll write it a little bit differently. You see, so we put the ZOH over here, the transfer function, and the ideal analog to digital conversion, and the overall chain is now modeled by this transfer function, but the interpretation of course stays the same. So we'll apply this zero order halt method to our system, which is first order and has static gain 1. We have to compute the step response. So in the Laplace domain we multiply by 1 over s. This is what you have to obtain. Then you do a partial fraction expansion, right? Very easy. You hide this one, you replace s by 0, you have a 1. This is what you have. For the term here, what s plus a on the denominator, well, you hide this one and you replace s by minus a, and you have a minus 1. So this is indeed correct. Well, you can check by putting everything under the same denominator. So if you do the inverse Laplace transform, you'll have the step response, and it will be 1 minus the exponential of a t times u of t, right? So if you sample this signal that we have obtained over here, this is what you obtain. So you have now a discrete time sequence, and you can of course obtain the z transform. Okay, so the z transform of uk is this one, and this is the z transform of uk, a step, and this is here with the minus sign over here, the z transform of the signal e to the minus ats to the power k u of k, right? And to obtain the step invariant or ZOH equivalent description, we have to multiply by 1 minus z minus 1, or z minus 1 over z. It's better here to work this way because we work with the variable z. You put everything under the same denominator. You will see that this one and this one will cancel out, this one and this one will cancel out, this one and this one will cancel out, and this is the equivalent description in discrete time of the initial transfer function using either step invariance or the ZOH method. You can see here now that the static gain of this transfer function is indeed 1. Remember that you replace z by 1, and obviously here the static gain is 1. This is kind of, well, logical, because we have imposed that the step responses will have to coincide at the sampling instance, so therefore the static gain must coincide as well. So what we can do over here is again do the calculation with the Matlab symbolic toolbox. You define the symbolic variables, the transfer function. This is the step response because we take the inverse Laplace transform, we sample it, we replace t by nts, right? Then we take this response and we take the z transform, we multiply by z minus 1 over z, and you obtain the same results as obtained in the slide. Remember that this will allow you to obtain a ZOH equivalent discrete process for any process, but depending on the variables and on the sampling period, and this might come in handy in some situations. So again, we can test our results in Matlab. So this is our transfer function. H of s is a over s plus a. We've chosen the same a and ts. This is how you introduce or code the system in Matlab. Of course, what you could do is use the command c to d, and if you're interested in the step invariance, or equivalently to the interested in the ZOH method, you have to use the argument ZOH. As a matter of fact, if you do not use an argument, it will still use the ZOH method. So these are the numerator and denominators of the transfer function that we have obtained. So we kind of obtain here the discrete time description, and then we compare step response and impulse response for the original system and, well, the equivalent discrete time description. So here in blue we have the continuous time impulse response, and here in orange we have the impulse response of the discrete time equivalent description, and as you can see, they do not match at the sampling instance. We will see that when ts will be decreasing, the difference between the discrete impulse response and the continuous impulse response will become smaller and smaller. So here we have the step response in continuous time in blue, and we have the step response, the discrete time step response of the discrete time equivalent using the step invariance or ZOH method. These two methods are the same, and as you can see, at the sampling instance, right, these step responses coincide. This is normal because we have imposed that these step responses must coincide. Well, this is the code that you have just seen. If we run the code, well, you obtain the same step and impulse responses. What you can do is now divide ts by 10 and rerun it. As you can see here, still the step response matches at the sampling instance, and you see here that the static gain is of course the same as in the continuous time case. And now you see here in the impulse response that the match between discrete and continuous time impulse response has improved, with theta s becoming smaller, but still it's not an exact fit at the sampling instance. If you divide by 10 over here again, you can see here that, well, there's still a difference at the sampling instance, but as TDS has decreased, well, the match between the discrete time and continuous time impulse response becomes now almost undistinguishable. So in this case, if you use the step invariance or ZOH method, you will have step responses that will match at the sampling instance, whatever the TS. The impulse responses will not match in general, but as TS will decrease, well, the mismatch will become smaller and smaller. We will do now an exercise where we have to find the ZOH equivalent discrete time description of a given transfer function. This is the type of exercise that you might have at the time of the exam, or either with this method, so the ZOH equivalence method, or any other method for a particular system. The transfer function that we're considering is that of a lead lag system. So here you have the lead time constant and here the lag time constant. And as we've said, we are looking for the ZOH equivalent description. right? First thing that we have to do is to find the step response. We multiply by 1 over s, as you can see over here. To obtain the inverse Laplace transform, we'll have to perform a partial fraction expansion over here. I won't go into the details, but the parameters a and b are obtained like so. This is something that you have to be able to do after last year's course of signals and systems. So if we take the inverse Laplace transform, we obtain this expression. This first term comes from the first term over here, and this second term comes from this term over here. So what we do now is sample the signal. So we simply replace t by kts, and we rewrite it a bit so that we are able to take z transforms. To obtain the ZOH equivalent, we have to take the z transform and multiply by z minus 1 over z. So the z minus 1 over z is over here. The z transform of 1 time uk, it's z over z minus 1, and the z transform of this one times uk is given over here, and of course you have the factor that you have over here. If you simplify, this is what you obtain, and then what you can then do is, well, put everything under the same denominator, and this is what you obtain. So if we have a look at the poles in continuous time for this description over here and for the ZOH equivalent, we arrive here at that the continuous time pole is equal to minus 1 over t2, and as you can observe over here, the discrete time pole is equal to exponential of minus ts over 2. So indeed the poles are mapped by the relation exponential of TSS. So the discrete time pole is the exponential of TS, the continuous time pole. This is something that we had discussed previously. So where can you see the discrete time pole? Well, you can see here at the numerator, and I've written its expression over here. So this is the discrete time 0, the continuous time 0, zc is equal to minus 1 over t1. So here we do not have this relation between the continuous time 0 and the discrete time 0, but you can observe that if ts is small over here, and remembering that the exponential of x is approximately 1 plus x, right? You inject 1 minus ts over t2 to replace this exponential. You end up with this expression over here, right? So this is equal to that, and this is approximately the exponential of minus ts over t1. So if you take the continuous time 0 and you assume that ts is small, then again the 0 in continuous time and in discrete time are linked using the relation z is equal to tss. So you can approximate the 0 by the exponential of ts times the continuous time 0. But again, this is only true when ts is small, because when it is not, you can see indeed that this relation is not valid. We can check our result in Matlab. So here we have the lead lag system. We take t1 is equal to 1 and t2 is equal to 2 seconds. We take a sampling period of 0.5 seconds. So here is what you obtain using Matlab. So this is the C to D command with the argument ZOH. This is what we had obtained. Okay, so we define the variable z and construct the transfer function, we assign a sampling period ts of 0.5 seconds as follows, and then we take the step response of the original continuous time systems and the two discrete time descriptions, the one obtained with Matlab and the one that we had obtained, and we take a step and we look at the first 10 seconds. And this is what you obtain. You can see that this is indeed the ZOH equivalent, or the step invariance equivalent, because the discrete and continuous step responses coincide at the sampling instance, and you observe that what we had computed corresponds to what Matlab proposes as a solution. The next method is the match poles and zeros method. So the idea is to use the relation z is the exponential of TSS to map poles and zeros to discrete time poles. So you take the continuous time pole, and the discrete time pole is obtained by this relation over here. You know that this is the case with any method, but we also impose it for the zeros. So the discrete time zeros are obtained from the continuous time zeros by this relation. And then the DC gain, low frequency gain, or we call it also static gain, is adapted in such a way that the two transfer functions have the same static gain. Well, remember that most physical systems have more poles than zeros. There is a pole zero excess D. Okay, so this is something that we have seen. So you have a zero at infinity. Well, the idea here is that this zero at infinity is mapped to a zero at z minus 1. This results in a factor 1 plus z minus 1 in the numerator. And you can see this as kind of averaging the current and the past input values. Another alternative would have been to see these zeros at minus infinity and to replace them by zeros at the origin. But most often in this method, it's this alternative that is chosen. So the zeros at infinity are replaced by a zero in minus 1. Well, very often, and this is the approach that is followed in Matlab, if there are several zeros at infinity, well, all the zeros will be mapped to a zero at minus 1, except one that will be mapped at zero at infinity. In such a way, we'll have a delay of at least 1 in the system. So let us apply this to our system. First order system with DC gain or static gain 1. We have a pole here that is minus a, so the discrete pole will become exponential of minus a ts. This is what you see over here. We have a zero at infinity. If s tends to infinity, the transfer function tends to 0. So this 0 at infinity will be replaced by a 0 at z is equal to minus 1. This is what you have over here, and then we have to adjust the gain in such a way that the static gain of this one coincides with the static gain of this one. Right, the static gain of this one, well, you take the transfer function and you evaluate it at z is equal to 1. This is what you have, and you have to impose this to be 1 because this is the static gain of our original transfer function. So without too many difficulties, you see here that this is the k that you have to choose. This results in a transfer function when, well, the degree of the numerator is 1, and this is also equal to the degree of the denominator, right? So there is kind of a direct transfer term, and well, very often we prefer to have a description with a delay of at least 1, and this will be the method followed by Matlab and the one that we will see in the next slide. So in this method and used by Matlab, well, all zeros at infinity are replaced by a 0 at -1 except 1, but of course here we only have 1 0 at infinity, so it will be replaced here by a 0 at infinity. For the pole we do exactly the same thing. Okay, so indeed here we see that we have a 0 at infinity. If you replace this transfer function with z is equal to infinity, the transfer function tends to 0. So we have indeed a 0 at infinity, but this allows us to have a 1 period delay in the system, because you can rewrite this as follows. Okay, so you have clearly here a delay in the system. If you write this as yz over xz, what you will have is that 1 minus the exponential of ats z minus 1 times yz is equal to kz minus 1 x of z. So yk, if you do the inverse z inverse transform, yk will be minus, and we'll take it the other side, so will be exponential of ats yk minus 1 plus k xk minus 1. So clearly there is a delay of 1 in here. Y depends not on xk but on the previous xk, right? So making sure that you have at least 1 0 at infinity if you have a pole 0 axis ensures that you have a 1 period delay. But apart from that, the method is exactly the same. We have to make sure that the static gains coincide, right, for the discrete time approximation and for the original transfer function. Here we had a 1. This is the static gain that we have now, and well, you can kind of see that you have to take k is equal to 1 minus the exponential of minus ats. And in this case, this is not always the case, well, this match poles and 0 methods, okay, with this 0 at infinity coincides with the 0 order hold equivalent, which itself coincides with the step invariance equivalent. As usual, we can test this in Matlab. This is our transfer function a over s plus a. We choose the same a and ts. We encode the system. This is the first match pole and 0 equivalent description. This is the second, right? You can run the command c to d with the argument matched, and it will give you the second match pole and 0 equivalent. And what we can then do is compare impulse and step responses in continuous time and for the two matched designs. So in blue the continuous time impulse response, and in orange and lighter orange you see the impulse responses in discrete time for the two designs. As you can see, they do not match at the sample instance, and you can see that the second design indeed introduces a delay of 1. Here you can see the step responses in blue, the continuous time step response of the original system, and in orange and lighter orange the discrete time step responses of the two matched designs. The second design introduces a delay of 1 as expected, and here in this case it also coincides to the ZOH equivalent discrete time system or approximate, or the step invariant approximate description of the system. This is why they coincide at the sampling instance. As a remember, this is how you can do the discretization using a Matlab. You have to use the command C2D. We use the same type of system as before, but here we have chosen A is equal to 10, TS is equal to 0.05 seconds. So impulse invariance, you use the argument impulse. Well, step invariance or zero order halt, because they are equivalent, you choose the argument ZOH. If you don't put any argument, it will automatically select this method, pole zero mapping, matched. And these are two methods that we will see in the next subsection on numerical approximation or numerical integration methods. What you can then do is compare the underlying systems, continuous and discrete, using a Bode diagram. So what we do here is compare the Bode diagram of the original system that obtained using the zero order halt discrete equivalent, and then one obtained using a numerical approximation method. So here a trapezoidal method. So here is the result of these Bode diagrams. In blue you have the frequency response of the original continuous time system, and well, in green and red the two responses for the discrete time equivalents. So obviously you cannot look beyond the Nyquist frequency. This sometimes comes as a surprise to students, but of course TS is equal to 0.05 seconds, right? So the Nyquist frequency is equal to pi over TS, and in this case this is 20 pi, so this is correct, right? So let us have a look at this zero order halt equivalent description. Remember that this zero order halt mechanism introduces a delay of minus TS over 2, right? So at the frequency 2 over TS, right, this is 40 over here, we should have approximately a delay, a phase shift of 1 radiant. Okay, so this corresponds to 57 degrees. So 10, 20, 30, 40. So over here, if we compare with respect to the original system, we see that this method indeed introduces approximately a phase shift of 57 degrees. So this is how you see here that this zero order halt mechanism is really taken into account in this zero order halt discrete description of the system. So if you're going to use a discrete description for direct digital design, you have to take this zero order halt mechanism into account, and this zero order halt equivalent description is the one that you should use.